Alright, hey everyone. Today we're looking at the powers of I and operations with complex numbers. So let's get started with the basics, right? What does I stand for? I is a useful tool mathematicians and scientists have come up with to help us solve negative radicals, right? So we can break up a negative radical into I times a positive number. So that's the purpose of it, right? It helps us make use of some things that not make sense with our normal math rules. So I is the square root of -1, as shown right here. What are some of the I basics, right? Well, let's take a look at the powers of I, and let's see how they operate. So I works in cycles of 4, and you'll see why right now. So if I to the 1, any number to itself is just itself. So it's just I, right? I to the 1 is just I. Again, what is I to the 1? I to the 1 is the square root of -1, which is the same thing as saying I. Now let's take a look at I squared over here. I squared is -1. So you get I squared equals square root of -1 times the square root of -1, which is just -1. If you really think about it, this is -1. Remember, square roots are to the 0.5 power times -1 to the 0.5 power, right? So same base, what do you do when you multiply? You add the exponent. So this becomes -1 to the power 1. So I squared is just -1. Now, let's take a look at I to the third, right? We can think of I to the third as I squared, which is -1, times I, which is the square root of -1. So -1 times the square root of -1, which is I, is negative square root of -1. I know, a tongue twister. All right, now let's take a look at I to the 4. I'm going to change it to magenta, right? I to the 4, we can think of as I to the 4, we can think of as I to the 3, which I have here, times I to the 1. Again, I get negative square root of -1 times square root of -1. And if you work out all the math, you're just going to give back 1. And because it's cyclical, the powers of I, it's called the I clock, right? Some people find that useful. At 12, you start at 1, I to the 0 equals 1. Then you go to I to the 1, which is I. Then you go to I squared, which is -1. Then you go to I to the third is -I. And the cycle resets, so I to the 4, right? I to the 4 equals I to the 0, which is just 1. It's a cyclical pattern. It repeats every 4. That's going to be very useful in helping us solve the problems. So let's take a look at some problems right here. Let's take a look at the first problem, I to the 9. What is that, right? How can I solve that? So what you want to do is you're going to take the power of I, 9, right? And since it's cyclical and it goes in cycles of 4, we're going to do 9 divided by 4. And you're going to get 2.25, or if you do it quick in your head, you're going to get 2 remainder 1. When think of powers of I, you just really care about the remainders. So all you care about is the remainder of 1 or the 0.25, right? So what I'm going to do here is, if you don't realize when you divide 9 by 4, you have a remainder of 1, what you can do is multiply the remainder. You can do 0.25 times 4, which gives you back 1, all right? I'm going to use this 1 here, right? Because it works in cycles of 4, I can say I to the 9 equals I to the 4 times I to the 4, right? So far, so good, right? Times I to the 1, yeah? So I to the 4, I know is 1. I to the 4 is times 1. And then times I to the 1, which is just I. So I to the 1 is the same thing as saying I to the 9 because they're equal. And mathematically, we saw that they're equal. So why don't you take a second, pause the video, and try to do number 2 yourself. Again, you're dividing by 4 to find the equivalent powers of I, right? All right, so let's take a look at number 2. First thing I want to do, I want to break down I to the 24. What I'm going to do is 24 divided by 4. Well, I'm going to get 6.0. So I have a remainder of 0. I have a remainder of 0. Or you'll get 6 remainder 0. There's no remainder when 24 is divided by 4. So what you can do is you can write equivalently, right? You could say I to the 24 equals I to the 4 times 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 I to the 4. And what do we know? I to the 4 is, as we learned back here, I to the 4 is 1. All right. I to the 4 is 1, so I to the 24 equals I to the 4, which is 1 times 1 times 1 times 1 times 1 times 1, which just equals 1. So I could say I to the 24 is equivalent to I to the 0, which is just 1. And I'm done with this problem. Almost. I forgot something. This 2 right here. So now that I know what I to the 24 is, I'm going to multiply 2 times I to the 24. But I know what I to the 24 is. It's just 1. So I'm going to do 2 times 1, which is just 2. And that's my final answer. Now let's take a look at the next problem. It says, let f of x equals x squared plus 2x plus 3. If x equals 2i, what is the output? So this is asking, so you're going to replace x with 2i right here. This is what this question is asking. So you're looking at f of 2i equals x squared plus 2x plus 3. So wherever you see I, because now this is the input of the function, you're going to put 2i instead. So let's do it. So I'm going to put, instead of putting x squared, I'm going to put 2i squared. Instead of putting 2x, I'm going to put 2i in parentheses. And I'm just going to bring the 3 down. All right. So 2i squared is 2 times 2 is 4. And I times I is I squared. Plus 2 times 2 is 4. There's nothing to do. The I is by itself. And I bring over my plus 3. All right. Again, what is I squared, right? What is I squared? Let's take a look back. What is I squared? I squared is -1. I squared is -1. So I can write, this is actually -4 times -1. Because I squared is -1. Plus 4i plus 3. Now, -4 times -1 is +4. So I have 4 plus 4i plus 3, which is 7. 4 plus 3 is 7 plus 4i. All right. Let's take a look at the next problem. If you want to try it yourself, go ahead. It's the same base, right? And it's all base. All right. Let's get back into it. Let's take a look at number 4. I to the 7 times I to the 5 times I to the 3 times I to the 0. The easiest way to do a problem like this is it's the same base, you just add up the exponents. So let's do that, all right? So this becomes I to the 7 plus 5 plus 3 plus 0. So 7 plus 5 plus 3 is 15. I'm not going to add plus 0 because any number plus 0 is itself. I'm going to get I to the 15. What is I to the 15? As we learned earlier, we're going to do 15 divided by 4, which equals 3 remainder 3, or 3.75. All right? So all I care about is the remainder here. All I care about is the numerical value of the remainder. So I can say I to the 15th, because they work in cycles and I already divided, is equal to I to the 3. And I to the 3 I know is negative I. And that's it. I'm done with the problem. There's nothing else to do here. Let's take a look at something a little more complex. Adding and subtracting complex numbers. All right? So what I have over here is 2xi plus 15 plus 5x plus 3i. All right, so what do I do here? Well, now I have to do what? Usually, when you see one of these, you have to express it in a plus bi form, right? So the way you add these is you want to put all the I terms together, and you want to put all the terms without I together. So let's take a look at this, right? So what terms have I? So I'm going to take this and take this, right? And it looks like a plus bi. So the imaginary numbers go to the side, right? So I'm going to have 15, or I'm going to put 5x first because there's a variable there. 5x plus 15 plus 2xi plus 3i. All right. Now I'm going to factor out something so it looks a little fancy. 5 and 15, they both share 5, right? So I can factor out a 5. So I can write 5x plus 3 plus, again, what can I do here? What do they both share? They both share an I. So I can factor out an I. So I get I times 2x plus 3. That's it. I'm done. All right? You might be asking, why can't I add the 3i and the 2xi? It's because this is an xi, and this is just I. So they're not like terms, so we can't actually add them together. If there was another term here, say maybe minus 4xi, then we'd be able to combine these two because they both have xi. But that wasn't in this problem, so we couldn't do that. Let's take a look at the next problem. Why don't you try it yourself and take a pause and see if you could do it. All right. So let's try doing this. Again, I'm going to rearrange everything. The i's with the i's and the non-I numbers, which are just real numbers, and by itself. So I'm going to put the real numbers first. All right. So this is the only real number I see, 36. So I have 36. All right. Now I'm going to put all the other, we'll put it in blue. I'm going to take all the imaginary numbers. All right. So I'm going to do plus 12xi. So I'm done here. Plus 4xi. I'm done there. Plus 8i. Done there. And minus 6i. Minus 6i. All right. Okay. So now I can see all of these have one in common. These all have I in common, and they also have something else in common. They have 2 in common, right? So let's take them out. All right, let's take out a 2 and the I from everything, so it looks like this a plus bi form up here, right? A plus bi. So I'm going to factor out a 2 from all these imaginary terms. I'm going to get 36. I'm going to keep that as is. That's my only real number. Plus 2i. Okay? I'm going to pull out 2i from both. Okay? 4xi plus 12xi is 16xi. So, instead of doing 16xi, I'm just going to do 8x. All right? And then I have here 8i minus 6i, which is, I can combine this, which is just 2i over here. All right, so 8 minus 6 is just 2i. And instead of doing subtracting 2i, I'm just gonna subtract 1, because 2i times 1, positive 1, will just give me 2i, which I got here. The next problem is a little more complex. As you can see, there's powers of I, and I'm adding and subtracting everything. So, again, what is the first thing we should do when you see a problem like this? Even before you rearrange everything, you want to break everything down, right? Because you want to know what these powers of I are going to resolve into. So we're going to resolve this first and then rearrange everything. So first thing I'm going to do is do I to the 10. All right, how am I going to work with that? That's going to be 10 divided by 4, which is going to be 2 remainder 2. So I to the 10 is the same thing as writing I squared, which is negative 1. All right? So that's just I to the 10. Now let's look at I to the 19. I to the 19, I'm going to, since it works in cycles, 19 divided by 4 equals 4 remainder 3. So I could say I to the 19 is the same thing as writing I to the 19 is the same thing as writing I to the 3, because all I care about is the remainder, which is the same thing as writing negative I. All right? And over here we have another I to the 3, and we know I to the 3, again, equals negative I. All right? So now I'm going to plug in these values here. These values I found instead of I to the 10. I'm going to plug in negative I instead of putting in I to the 19. And instead of putting I to the 3 for this 2i to the 3 term, I'm just going to put in negative I. All right, so let's go. So I'm going to do 4x, and instead of writing I to the 10, I'm going to put in negative 1, because that's what I to the 10 is. Negative 1 minus 12y. Now I'm not going to put I to the 19. I'm going to put in negative I. Negative I. All right. Then I'm going to do plus 2y, not I to the 3. Again, I to the 3 is the same thing as negative I, so I'm just going to do negative I. Minus 3xi. All right. So let's see. 4x times negative 1 is negative 4x. Negative 12y minus negative I. So negative times negative is positive. Negative times negative is positive. This cancels out. This cancels out, right? And 12y times I is just 12yi. Then I have positive 2y times negative I. So positive times negative is negative, and all I have left is 2yi. And over here, I just bring down my 3xi here. All right, now I'm going to put all the terms with I and all the real terms that don't have I. Well, lucky for us, lucky for us here, they're already kind of arranged this way, all right? So I have negative 4x plus 12, negative 2, negative 3. They don't share anything in common, but they all do share an I, right? They all do share an I. They all do share an I. All right? So 12yi minus 2yi is 10yi minus 3xi. So that's these two terms together. Now to make it look all nice and fancy in a plus bi form, I'm going to factor out the I here. So I get I 10y minus 3x. And that's my final answer. Now let's take a look at some multiplication and division problems. All right? For when we're dealing with complex numbers. So it's asking what is the product of I squared and 5x minus 2i squared. So this actually means I squared times, product means times, 5x minus 2i squared. All right. First things first, what does I squared stand for? It stands for -1, so I'm just going to replace it with -1. Now this is 5x minus 2i squared. So this actually means 5x minus 2i times 5x minus 2i. All right, I'm going to leave the -1 alone for a little bit. First, I'm going to FOIL, right? 5x times 5x is 25x squared. 5x times minus 2i is 5 times 2, -2 is minus 10. X times I is xi. -2 times -2i times 5x, same thing. I'm going to get -10xi. And then over here, I have -2i times -2i. So -2i times -2i. Negative times negative is positive. 2 times 2 is 4. I times I is I squared. All right? And I'm going to enclose this in parentheses, and I'm not going to forget to bring down my -1, because that's what was I squared. All right. So a couple of things we still have to do. So now I'm going to do is what combine like terms, right? Combine like terms. So I'm going to have -1 on the front, 25x squared minus 10xi minus 10xi is minus 20xi, and 4i squared, right? 4i squared. Well, what's I squared? I squared is -1. So 4 times -1 is -4. All right? So instead of writing 4i squared, I'm just going to write -4. All right? I'm almost done with the problem. What I have left to do is distribute this -1 that came from I squared. So -1 times 25x squared is -25x squared. -1 times -20xi squared is negative times negative is positive. So I get positive 20xi. And -1 times -4 is positive 4. Now I want, now to make sure everything's proper, I'm going to do the a plus bi form. I'm going to put the real numbers up front, and I'm going to put the complex numbers or imaginary numbers in the back. So I'm going to do -25x squared plus 4 plus 20xi. Right? So it all looks kind of arranged. Last type of problem for most of the complex number operations you'll see for the Algebra 2 regions is you'll be asked to simplify, right? You'll be asked to simplify something like the square root of -128 over the square root of negative 32. So first thing I want to do, I want to break down the square root of negative 128 into the square root of negative 1 and the square root of 128 over the square root of negative 1 times the square root of 32. All right? Now I can work with this, right? I can work with square roots of positive numbers. I can't work with square roots of negative numbers unless I pull out this negative 1, square root of negative 1, which stands for I. All right, so let's break down, first thing, let's break down the square root of 128. All right, let's break this down. So first thing I'm going to do, I'm going to see if 128 is divisible by 2. It is, so I'm going to get 128, which is the same thing as right at 64 times 2. Well, lucky for me, I can break down 64, right? I know my times table. 64 I know is a perfect square, so I can say 8 times 8 times 2. And when you have the same two numbers in a square root, they come out, right? One of them comes out. So I have left with 8 square root 2. And that is the square root of 128. Now, I'm going to look at the square root of 32. I'm going to do the same thing. I'm going to divide it by 2. So I'm going to say 32 is the same thing as writing 16 times 2. Oh, I got lucky again. I know 16 is a perfect square. It's 4 times 4 times 2. Same thing, 2 of the same number, I can take it out. So the square root of 32 is the same thing as writing 4 radical 2. That's the square root of 32. All right, so now let's plug this back into the original equation right here. So what is the square root of negative 1 over here? It's I, right? And what is the square root of 128? 8 square root of 2. All right? Over, again, square root of negative 1 is just I. And then square root of 32 is 4 square root of 2. Well, it seems like there's a lot of things that I can cross out, all right? A lot of things I can simplify. The i's, they cancel out, right? And then I have square root of 2 and square root of 2. That cancels out 2. And then 8 is divisible by 4. So this cancels out. The i's go away. The square roots go away. 8 over 4 is 2. So my final answer I get in the end is 2. That's it. That's my final answer. And that's how you simplify radicals, negative radicals, which use complex numbers and imaginary numbers. Good luck on your slip. Have fun.